High-Speed Amplifiers Part 2 by Analog Devices. Welcome to the training module on Analog Devices High-Speed Amplifiers Part 2. This module introduces the effect of PCB layout for high-speed performance. Bypassing is essential to high-speed circuit performance. Capacitors right at the power supply pins provide low AC impedance to ground and local charge storage for fast rising or falling edges. Keep traces short to minimize inductance. Trace inductance and bypass capacitors can form tank circuits, which causes resonance. The resonant frequency can be determined using the equation shown. A 1 microhenry trace inductor along with a 0.1 microfarad series capacitor will resonate at 500 kHz. A small series resistor can be used to dampen the Q of the circuit and prevent oscillation. Be careful because using a very large resistor value will have a large voltage drop across it. Keeping the load and bypass capacitors ground return close together will improve performance and can lower distortion. Reduce the length that the return current has to flow from the amplifier to the load to help minimize any interference with other currents circulating in the ground plane. Use multiple bypass capacitors in parallel to keep impedance down across a wide range of frequencies. A good place to start is with a 0.1 or 0.01 microfarad capacitor for the higher frequencies. For the lower frequencies, a 2.2 to 10 microfarad electrolytic usually does the trick. Values are usually determined empirically and will be set by the circuit requirements. You can see that a 2.2 microfarad, a 0.1 microfarad, and a 0.01 microfarad provides a very good low impedance of 0.1 ohms from 1 MHz to 40 MHz. It is important to provide a low impedance as this is the only way to prevent undesirable noise from entering the system. SMT ferrite beads are another very effective way of reducing high-frequency noise from entering the board and have virtually no DC drop. The American Heritage Dictionary defines parasitics as organisms that grow, feeds, and is sheltered on or in a different organism while contributing nothing to the survival of its host. We can think of these parasites as little gremlins that quite literally wreak havoc on circuits. They rob us of circuit performance and do not contribute anything to the overall performance. Parasitic capacitors are formed between component mounting pads and ground planes. Parasitic inductance can be formed in long traces. Parasitic resistance can be formed in ground planes. The image shows some parasitic elements in a PCB. This is an illustration of how parasitic capacitance can be formed. The equation for calculating the capacitance is also shown. Removing all ground and power planes underneath any op-amp input pins is recommended. This reduces the parasitic capacitance on all pads, which is especially important as the summing node of the amplifier, -IN. Remember that a parasitic capacitor or a -IN reduces phase margin and stability. Here is an example of a parasitic pad capacitance for SOIC pads. There are a few ways to reduce parasitic capacitance, such as increasing board thickness or layers, reducing trace or pad area, and removing ground planes. A ground plane minimizes parasitic inductance. It provides a return for the current, and the bypass and magnetic fields cancel each other, thereby reducing inductance. Making a short trace is more important than making a wide trace. This is an example of a parasitic trace inductance. There are a few ways to reduce trace inductance, including using ground plane, keeping trace lengths to a minimum, and doubling the width. Even if vias can introduce parasitics into a circuit, it doesn't take many vias to start to accumulate parasitics. Multiple viases can help lower inductance, but they will increase the capacitance. It's a trade-off, and each design has to consider which option is best for the application. This is a cross-section of a wire that shows the dimensions of the features from the previous slide. When you buy a resistor or capacitor, you're getting more than just a resistor or capacitor. You are getting the parasitics that come along with them. The complete capacitor model has resistance Rs and Rp. Rs is the ESR of the capacitor, and it is combined equivalent of Rs and Rp, which is the AC resistance of the capacitor. Rp is the insulation resistance of the capacitor. It is a measure of the amount of DC current that flows through the dielectric of a capacitor with voltage applied. Rp is typically 1000 megaohms or more. RDA and CDA represent the capacitor's dielectric absorption. The L represents the capacitor's series inductance. This is fairly big for leaded devices, but fairly small for surface mount devices. Here is the complete parasitic model for a resistor. Notice that it has a lot of the same types of parasitics as does the capacitor. This is a simple low-frequency schematic of an amplifier in a non-inverting configuration. If we take into account all the high-speed parasitics for each component, the simple schematic is no longer so simple. There are all kinds of new elements introduced to the schematic. This is sometimes referred to as the hidden schematic. If we don't address the parasitics, it can derail the entire design. In high-speed amplifiers, capacitance on the input and output can cause stability issues. This shows the effects of a few picofarads of parasitic capacitance on the summing node of an amplifier. You can download a free SPICE tool from National Instruments to simulate the effects of parasitic capacitance at the negative input of an amplifier. This is a schematic using the AD8055 amplifier. It is set for a gain of +2. A 2 picofarad capacitor has been placed on the schematic to your left and no capacitor on the schematic to your right. Let's take a look at the effects of a 2 picofarad capacitance on the inverting input. As shown in the parasitics section, 2 picofarad is very easy to generate. Just a few viruses can produce 1 picofarad quite easily. As you can see, running a Bode plot of the circuit produces almost 2 dB of peaking from that single 2 picofarad of capacitance. The next few slides will introduce the effects of parasitic trace inductance. This example has placed the equivalent of a 1 inch or 2.54 centimeters of trace inductance for a value of 29 nanohenries. We get a sustained ringing throughout the duration of the pulse, which is not a good thing. It does not take much to ruin circuit performance. This introduces what a small change in the circuit layout can do to circuit performance. The AD8009 is used, which has a bandwidth of 1 GHz. Shown are 2 different evaluation boards with slightly different feedback paths. The board on the left, circuit A, has a feedback path which is longer than that of circuit B. It's a small difference, but let's take a look at what the performance looks like. This is the wrong way to take high-speed measurements using the long ground clip lead. It represents a lot of inductance and can create ringing and overshoot. This is a transient response seen using a not-so-good clip lead. Notice the ruggedness of the pulse as well as all the ringing. Shown on this slide is the right way to make measurements. Get rid of the probe outer plastic shield and a ground clip. Make the ground contact right on the probe ground. This is shown with the oval in red. No inductance or very little inductance results in a nice clean pulse response. Here are the results of Circuit A and Circuit B using the proper method for picking up the scope probe ground. You can see there is a 25% reduction in overshoot and ringing. Ground and power planes can provide a common reference point, shielding, lower noise, lower resistance, lower impedance, reducing parasitics, heat sink, and power distribution. Ground plane helps reduce inductance by canceling the magnetic field. Inductance is defined as the energy stored in the field set up by the current that travels in a wire. Here is an example of the wrong way to set up an analog and digital or mixed signal PCB. This method has analog and digital sharing a common ground, which will lead to noise in the ground and produce errors in the circuit. In the schematic, the current flowing in the ground inductance will generate noise voltages. The currents going back and forth between the two digital chips will severely corrupt the analog signal. This is the right way to do it. Notice the analog and digital sections are isolated. The digital current flows back and forth between the digital parts, and the analog circuitry is by itself. Here's another grounding example. Here's an optional layout for analog and digital circuits. Notice that there is one and only one connection for the grounds. This is a star ground, which minimizes the interaction between analog and digital circuits. Also note that the analog power supply is returned to the analog ground, and the digital power supply is returned to the digital ground. When using a mixed signal device, make sure that the grounds for it are tied to the correct grounds as shown. These are some ground plane recommendations to follow in your design.